can do this because 2n plus 1 is less equal m, so 2n is in particular less equal m. And now, well, f cross f is certainly an immersion into m cross m. So what is the image of f cross f intersected with the diagonal of f in f? Again, by transversality, I can make sure that they intersect in a sub-manifold of dimension this plus this minus the dimension of the ambient manifold. So the dimension of this is, what is this? So this is 2n, and this is m plus n minus 2n. Well, 2n minus m, and this is less than 0. So double points. So this is actually this is the set of double points. Okay. With a similar proof. Given an immersion, the middle dimension immersion, this is homotopic to a self-transverse immersion. To a self-transverse. So how do you prove this? Using transversality again. So now I have to remove the triple points. So let delta 3 be this sort of diagonal. Now I look at the image of the image of f cross f cross f intersected the image of delta 3m. So this is the triple point set of f. Yes?
Why does it not make any immersion? Sure. So the condition, the embedding condition is 2n plus 1 less than
well, if it's 0, then you have actual, it's 0 dimension, so you have points. You have double points.
Oh, okay. Okay, yes.
Okay, so similar consideration. So I can make the image of f cross f cross f transverse to this. This is not a manifold here, by just a small remark. This is clear what is meant by this. The image of an immersion is a union of manifolds, so I can make this union transverse to something else, to a submanifold, or to another map by the same theorem, basically. Okay, so what is this dimension? Well, again, so the sum of dimensions minus the dimension of the ambient manifold. So this is 3m minus m minus 3m plus m minus 3m, so 3m minus 2m. Well, and what is m actually? Well, m is 2n. This is 3n minus 4n, so minus n, in particular less than 0. So I can remove, by transversality argument, I can find another map F which is homotopic to the previous and doesn't have any triple points, and then, well, and now small perturbation ensures that all double points are transversed. What was the notation? Self-transverse. Transverse, I think. Okay. This is the proof so far. Any questions? So we have still to prove the second part of the Whitney embedding theorem, stating that if the dimension condition is 2n less equal n, but the target manifold is simply connected, then that I can still get an embedding. So in other words, I can, when the target manifold is simply connected, I can remove all the double points. I will prove this at the end. Okay. So in the next part of the talk, I'm going to talk about algebraic and geometric intersections, and well, in the simply connected case, it's an intersection number. In the non-simply connected case, it is an element of the group ring of pi 1 of the manifold. And just a small remark, because we didn't really talk about this so far, but to ignore this at all would mean to talk about simply connected surgery somehow. I mean, we were ambitious and wanted to keep it hard in the seminar. So I mean, this is just a remark. Recall. So if I have a map of CW complexes, then F is a homotopy equivalent. I mean, why does this matter? Yeah, the usual surgery setting will be a map from a manifold to a geometric concurrent complex, and then we will try to kill the surgery kernel, so elements in the relative homotopy group, to ensure that the map is a homotopy equivalence. So, and it is a homotopy equivalence if and only if, well, there's an isomorphism on the fundamental groups, and it is an isomorphism on the covers. Well, homology isomorphism on the universal covers. And this is why we basically always operate on the universal covers. Yeah, and for the homology, universal cover, we still have the, well, we have a Poincare duality statement. This is the universal Poincare duality, where we cap with a fundamental class which leaves the homology of the manifold or the homology of the orientation cover in case the manifold is not oriented. Okay, now a bit of notation. So a map from manifold n to a manifold m is called I1m trivial if it is 0 on the fundamental group. So what does it mean? It means here's the universal cover. Here is another projection. Here's F. We can pull it back, the cover. Since the map is trivial, this is a trivial cover. And so of course we get the lift here. We also get the lift here. Well, because of this condition. And this lift is unique if you work in a base context, because then we know that the base point of m goes to the base point of m tilde. Okay. Next definition. Well, okay, no, just so let us denote by n the push forward of the fundamental class of n. So this is a class n. Or the push forward of the fundamental class of n under the lift f tilde. This lives in homology. Well, the universal cover. Okay, so the algebraic intersection